This question asks for the electric potential in the vicinity of a spherical insulator with charge Q and radius R. So just like we did in class, we did the conductor, we did outside, at the surface, and inside. We'll do the same thing for the insulator. So we'll start with our expression for the electric potential. So we're starting with outside. So our distance R that we're finding the potential is bigger than the radius of our sphere. Here's the radius of the sphere. Start with our expression for electric potential, delta V. So delta V means a change of potential between 2 points. So VB minus VA. We'll take B to be a point right here. We'll take A to be a point out at infinity. So, and then B is at a distance which we'll call RB. So our change of potential is minus the integral of E dot ds. Just like we covered in class, the integral of E dot ds is the same as the radial component of E, the only component, times dr. So we have minus ER times dr. There's our integral. And we'll put in the limits of our integral. So we go from point A to point B. At point A, the distance is equal to infinity. And at point B, the distance is RB. So let's put in the expression for the electric field. Outside of an insulator, the electric field is KQ over R squared. Integrated with respect to dr from infinity to some point RB. We'll take our KQ outside because those are constants. So we have 1 over R squared times dr. The integral of 1 over R squared is minus 1 over R. Whoops. Is minus 1 over R. That's evaluated at RB and infinity. So let's put in those limits. So minus times minus gives us a plus. We get KQ 1 over RB minus 1 over infinity. 1 over infinity, that's just 0. And RB, instead of continuing to write RB, why don't we just let that be some general distance R? So KQ over R. So outside the sphere, the electric potential as a function of distance from the center is equal to K times Q over R, as long as we set our reference point to have a potential of 0 at infinity. Okay, now, let's include our reference. V at point A is V at R goes to infinity equals 0. So let's also do at the surface. At the surface, we'll call point C. So R of point C is equal to R. We know as we come inwards, it has to stay continuous. So at surface, it has to stay continuous, so it has to have a value that carries on from what we had at point B. So VC, the electric potential at the surface with regards to our reference point, is the electric potential at a distance of R equals the radius of the sphere, because that's at the surface, equals K times Q. Instead of R here, we have capital R for the radius. So there's the potential outside, there's the potential at the surface, and in the next video we'll do the potential inside.